my name is Rafael Taubinger, and this video is about getting started with C, C++, C# and Java for embedded systems and apps in IAR Visual State. IAR Visual State is a tool for design and code generation. It is used to graphically design state machines and generate C, C++, C# and Java source code for embedded systems and smartphone desktop apps. State machines is a commonly used abstraction that is used when programming state-driven applications, where systems behavior is a function of both input and current system state, like user interfaces with complex priorities and animations in HMI systems. With IAR Visual State, you can speed up time to prototype and shorten your time to market. At the same time, you ensure the code quality and smart features enable you to organize and modularize your design for efficient teamwork. Embedded systems and apps are built in large and distributed teams with different skills. State machines are often used as a common language that everybody in the team understands, from beginners to experts. IAR Visual State is also an excellent tool for design tasks dealing with functional safety. The functional safety standards, for example IEC 61508, recommend state machines as one design method for mid-higher SIL levels. Applications that benefit from IAR Visual State solving and handling complex state machine systems include automotive applications like instrument clusters, self-driving vehicle systems, advanced power tools, vending machines, HVAC systems, tracking systems, elevators, and finally, PLCs and control systems. Some of the extended capabilities worth to mention that are also displayed on the screen are suited for low-code development in embedded systems and apps development. Generates very compact code, and it's architecture agnostic, 8, 16, 32, 64-bit, doesn't matter. The C, C++ code is MISR C compliant, and Java and C# is a great fit for apps development. It's based on UML, Unified Modeling Language. Support for hardware debugging with direct feedback in the state machine design. It's tightly integrated with IAR Embedded Workbench, but works with any compiler, of course. It automatically generates documentation. It includes tools for advanced validation and verification. And of course, additionally, there are plenty key features that we should mention, like cross-platform support running on Ubuntu and Windows. Support for variant handling is also available, so you can build different variants from the same model. There's a hierarchical coder available to improve code size and speed efficiency from the generated code. You also have a diff tool for comparing changes in the state machine in XML, GUI, and even file level. It supports, of course, multiple users. And there is also support for requirements. So the designer has the support for importing requirements from the standard rec-if format, and the designer can mark items as fulfilling selectable requirements. There's also XMI import-export, so it allows you to import-export state machines from standard XMI and exchange these models, yeah? And of course, way more. So let's move into practice so you can get a feeling on how all this comes together. So I have here IAR Visual State open, and the way it mainly works is that you start with your model. I mean, there are various elements that are available. I mean, from simple states, composite states, various transitions or some variants like self transitions, initial state, history states, final state, join, fork. So that's all, of course, available. So you can set up the logic. And the way it works is actually you will be able to use low code development here, because you create graphically your state machine here, and then later the idea is to mainly integrate this generated code with some low-level drivers that might be already being generated by the various silicon vendor tools that can do that. I mean, Hall or BSP drivers and so on. And then you just build it and have your system running pretty quickly. But aside of the different elements here, there are also some transition elements that you need to be aware. I mean, you will have events that you can have, like in this case I have some timers, cars timer, pedestrian timers, and what you are going to do here, it's mainly a crossroad, and we will control the lights for the cars and then for the pedestrians. So that's why we have these different elements here, and even a button. I mean, if the pedestrian wants to cross, he can press that button to get the light open to cross in a safe way. But additionally, of course, there might also be some action functions. I mean, while changing from one state to other, you might be willing to have some actions that happen in this transition. And then this is, of course, the way you do it. If you maybe have some variables like here, you can even declare them here. And then once you have them all, you can use them in the model. You might be wondering what happens if you have some BSP that someone else generated, or even a silicon vendor. How does that work? There's a simple way to just use the header file and import that, so you have it all available here to be used. Good. So once you have your state machine in place here, you might probably be willing to do some simulation or some testing. So that's easily done here with simulate project. I will start it here, and hopefully I can fit the windows in a good way. Yes, so that's probably here in a good way. It might be a good idea to use multiple screens, of course, also. But the way it works, I mean, I will start it here, send just a reset, and on the right side you can see that some things are already happening. And I mean, if the pedestrian button is pressed, so it will of course start to do some changes here. The timers of course can also be triggered, and as you can see, the state machine is reacting. From here, of course, you could do even a bit more to record a sequence and then repeat it again. So it's a good test for setup. But even without having any hardware, you can just make sure that your state machine, your model, is consistent. Yeah. Good. From here, the next step is instead of just going ahead and generating code, and I will also show you the options that you have, you should probably do some verification, so you can actually verify your system. So it will mainly check if there are some unused elements maybe, or ambiguity, some conflicting transition, dead ends that are actually dangerous in state machines. So you can be safe that your model is validated here and consistent. And that's really done in an easy way here with the verificator. Something that you should probably be aware is that you can also generate documentation. So how fantastic is that? So your full model gets documented in just pressing a button. And you have, of course, different options. You can add some additional information. But if I just scroll down here pretty quickly, you will see that the model is being documented here in a nice way. There is also some project signature just to make sure that the documentation is aligned with all your model and the generated code. But it's a very detailed documentation. You can, of course, have different levels, all transitions, the regions that are available. You can even change here the size of the pictures and everything. And if I scroll down here to the end, you should even have some more specific pseudocode, so you can see how it looks like here and what has been generating. So it's, let's say, understandable code. Good. From here, if I just move back here, we should probably go to the code generation, so we can move forward here. But maybe we should explore some of the options here in the code generation. And of course, you can generate some readable code. That's like the switch case statements that you can see. But it's up to you if you want to generate table-based code. But the options are available here. I mean, you can, by default, it's C code that is generated, but you can choose here C++, C#, or even Java. Of course, you can only generate one or other, but you just select what you want. And from here, it's mainly straightforward to generate this code, and I can probably just run it quickly here. And we should probably get some report here that the code is successfully being generated. Yes, so as you can see, the code was generated here, C++, we have a few files. Good, so this is the way it works, and of course you can see that you have all the possible combinations here. I mean, we support UML, so it's up to you to use your creativity and best solve a specific problem that you're trying to solve. From here, as I mentioned, you could use any compiler that's of course flexible and it's agnostic to architecture. In this case, I'm using IAR Embedded Workbench, and there are a few things that make it a bit straightforward here because of the better integrations we have. So first thing is, of course, if I look inside here on the options, we will see that there is a special plugin available here, and that's already selected. It's the IAR Visual State plugin under debugger, and you will see more what happens here with some graphical animations and so on. And the next step is every time you generate code, it automatically generates this IPCF. It's this project connection file from IAR systems, and if you add it to your project, it will populate it automatically with the necessary header files and C code, and that's what I have here. So if I just force it here to build, everything should be up to date, and we should be able to successfully build this project. So it's looking good. And what I can tell you is that when we talk about low code, where you still have to do a bit of coding, but not much, mainly what you need to do, you need to have some main with a while loop that mainly tries to check if there is any event coming in, and that event needs to be handled and injected into the state machine. So that's the code that you need to write here actually to make it work. And then of course what I'm using here is the standard peripherals provided by ST, so I don't have to worry about that. I'm mainly using the model from IAR Visual State, the state machine, and running this loop here. Of course, you could even use an RTOS, and that would be probably more optimized, so you could have many state machines running parallel, but you always have to look what makes it easier to solve your problem here. From here, what I can do, if I download to the target, we should enter here in debug mode. We build it successfully. The generated code with the vendor specific code and my simple main loop here. What you will see now is actually that we have some graphical animation popping up for us here, and I'm just waiting here until we reach main here. It's doing some synchronization, and as I said, we are here inside the main routine, and you can of course just step by step here run the application the way you want, but maybe I should just leave it running with F5 go here. And from here you can see on the right side that I'm running this application on my target now, and the states are blinking in different ways here. So what I have is this crossroad, and as I mentioned, I have a button that controls that. So if I press the button, we should see some changes here. Of course, there are some timers that need to be triggered, and then I can see here the LEDs changing. And as you can see, blue states, red states, what's the current state, and of course the cars are getting red now, and pedestrian has the way, or it's safe to walk. And of course, after some time, this will change back. So it's a very simple crossroad solved in a very efficient way with low code programming. And there are of course way more features that you can make use from the model side. As I mentioned, importing different models, or when you set breakpoints or look into registers in this scenario, you can even set breakpoints on the state machine level. So it makes it very handy and powerful to solve your problem in embedded systems. Or if you think that you can reuse the same code that has been generated here for the embedded system, you could maybe generate C# or Java and solve the problem of your app that maybe is going to be used in your smartphone. Great! As you can see, IAR Visual State can help you for sure to increase efficiency with graphical modeling. You can generate C, C++, C#, Java source code for embedded systems and smartphone desktop apps. The solution is well suited for dealing with functional safety and also well suited for low-code development in embedded systems and apps development that everybody in the team understands, from beginners to experts. So make sure to start your trial now. Just access IAR.com/Visual State for more details on how to get access to the evaluation version. The link is also being displayed on the screen now. Thank you so much for your time and hope to see you soon.